So we will be talking today about the magic behind the coroutines. And essentially, we'll start with this wonderful, incredible, disappearing coroutine act right before your eyes. And what we have here is, you already saw, it's Ubuntu LTS 16.04, forked Clang, and a trunk of an LLVM 4.0 from the trunk. So let's just start with the magic act. So you already saw coroutines earlier. By the way, how many people attended the morning talk by James? Oh, plenty. But just for those who didn't, I will wait. Where's the mouse? It did disappear. Okay, good. So let's start easy with the very small and simple coroutine. So we'll generate font size easily. I mean, we can keep going. So no, too early. So we will generate an infinite sequence of numbers. Okay, and then here we will consume it. Too much. Well, if it becomes too boring, I will just cut and paste. I already have it ready. Okay, Control V, Control B. Yes, you were right. Hold on. Oh, yes, it tells me right here. Good. So let's fix it. Okay, it compiled. You know, we go here, we'll print it, and it prints some infinite sequence of numbers. So, but infinite is not very convenient to work, especially with standard algorithm, because what I'm going to submit the coroutine to a standard algorithm like maybe accumulate. So we will add one more coroutine, which we'll call TakeUntil. Essentially, we will be taking values from a coroutine until it hits a particular sentinel value. Okay, so there will be some G, and then sentinel. And here we will do what we will expect him to do. We'll simply take this guy. Actually, we'll take G, not the gem, because we want to build a pipeline out of them. And here, if V is equal sentinel, we'll break out of the loop. And otherwise, we'll just yield whatever is being passed. And let's do here auto G equal gen. And then we will create another generator, will be TakeUntil. Let's say 10. And then we will print the result of this generator. Compile and run. Yep. Okay. So let's pass the generator to a standard algorithm. Now, maybe we'll do initially auto result, and we'll print it. So generator is a normal input iterable sequence. So it has begin and end. So we'll do this. Compile and run. And it will, I think, what? Sorry about that. And it's real. It's not so as to do. Of course, it has to have the initial value. Good. $45. So now the magic act starts. Well, first we'll see what's going on in the debugger. So we are here in the coroutine. Let's add a few more breakpoints in the beginning of this guy, maybe on the yield. And when we start, notice no breakpoints hit. Coroutines are started but not yet yielding the values. Only when accumulate starts pulling the values, we will actually jump inside and then jump inside here, yield the value. It shows some internals. Then we yield back, and we are inside of the accumulate, and we keep going. So, and if we go back to main, get rid of all of the breakpoints, and we'll go to main. No, not here. Wait. Okay. We can look at disassembly, and you will see, no, wrong button. This guy. Am I at the right place? In main. Well, it's a lot of code. You don't have to understand that. It's a lot of code, you know. Well, one more time, I want to show actually the actual code in main. Oh, I see. It's the end. It's because of the screen size. It now, let me make it smaller a little bit. So what you see here is that we create generator, we'll create TakeUntil, we'll call begin, we'll call end, then we'll start standard accumulate algorithm, and well, in the end, we run destructors. A lot of code, but it's pretty reasonable code. So now we're going to disappear this coroutine completely. First, we'll disappear printf, but I don't have to. Instead, I will just do return R. It's still something with a side effect, right? So we'll observe it in the disassembly. So now I'm doing the build release, which adds O2 to the command line. So now, let's go in. Okay, it stopped at the end. Let's look at disassembly. Wait. One more time. We saved it. We press Ctrl-Shift-R, build release. Yes, it says O2. Now, finally, F5. And we'll go to disassembly. And what we'll see is this. Where is the coroutine? There is no more coroutine. It's just a number. And by the way, we can keep piling on. We can add a few other transformers, but coroutine will end up being exactly that, just a constant. So our goal today is to figure out what are the transformations which make coroutine disappear, and also how you can make your own coroutine types which have this property that makes compiler to make coroutine again disappear into thin air. And what is left, the actual. Yes?
What if you put the first argument that accumulate stood par, will it still disappear?
One more time.
Put stood par there, does it still disappear?
Stood what? Stood
Stood par, P-A-R, does it still disappear?
Ah, okay. I haven't tried with that one, so sorry about that. Accumulate works, I know. Okay. Finally, let's get back to the slides. So in general, compiler looks like this. You know, in all textbooks, you have the front end, which does desugaring, which takes care of the high-level language, and then it transforms it into some intermediate representation, which is very good for the optimizer. And in this case, I'm showing LLVM IR. And finally, after optimizer is done improving the code, it goes to the code gen. So what would be a good place to implement a coroutine? So some languages implement them in the front end completely, like C# and Python. And we decided to experiment, what if we implement the meat of the coroutine here in the optimizer? And coroutine is just, at least in C++ level, it's a function with suspend points. When suspend point is reached, it goes back to the caller. And then there is some mechanism which allows to resume the coroutine. So in Clang, coroutine is lowered to LLVM coroutine, right here, retaining the same structure, because optimizers are very good at optimizing functions. They're not very good at optimizing state machines. So actually, we have two kinds of coroutines now. We have C++ coroutines, the one that you probably know, with await and yield, that are defined by this proposal. But we also have LLVM coroutines, which are a lower level, but they're still very awesome, and we're going to look at them a little bit. And they're defined by documentation at LLVM website in LLVM 4.0. And essentially, it's also just a function with a bunch of intrinsics. And those intrinsics tell us where coroutine begins, where it suspends, where it ends, and then there are two extra intrinsics which allows you to resume and destroy the coroutine. What it means is that not only C++, actually just one extra tangent, is that 2 years ago, we presented C++ coroutines of this kind for the first time. And I said that C++ coroutines are most efficient, most scalable, most open coroutines of any programming language in existence. So it is true, but maybe not for long, because potentially other languages can target LLVM IR and get those amazing, wonderful, disappearing coroutines that we saw earlier. And because LLVM coroutines are just a function with a bunch of intrinsics marking up the interesting points, we can actually do coroutines in plain C. And so that we don't have to learn today how LLVM IR looks, I'm going to demonstrate coroutines using C. So this is a C coroutine which generates an infinite sequence. So there is a score_begin macro, which is just a little bit of wrapper around the intrinsic. And we tell it, look, if you need to allocate memory for the coroutine, use malloc. And the coroutine will return me a handle to a coroutine frame somewhere, because there is some state which needs to be preserved when coroutine is suspended. Then at the end, we have appropriately named coroutend. And we will tell it, by the way, when you are done, use free to deallocate memory. And then we mark points where we would like coroutine to get suspended. So we have 2 suspend points here. And here is a usage example. We call the coroutine, it creates it, it returns us back a handle, and then we will loop 4 times and resume the coroutine. At the end, we will destroy it. After we send it through the optimizer, it will look just like this. Again, even in C, coroutines just disappear. So what do? We need to have some state which will be preserved while the coroutine is suspended, because stack is gone. And to build that state, we need to analyze use and definition and use of values. For example, here, n is used to initialize I. We look at the definition of n, and n is just an argument. And this green line does not cross a suspend point. If it doesn't cross a suspend point, we don't need to worry about it. On the other hand, I here, in the print, it goes into definition of I in the beginning of the for loop, and it does cross a suspend point. Thus, this value needs to be preserved in the coroutine frame. So we'll create a struct and we will put a value I in it. So once we build the coroutine frame, we will rewrite a function so that whenever you used to access the variable which has to go into the coroutine frame, we will be doing that from the struct. And that Coro begin, which gives us the coroutine frame allocated by malloc, possibly, we cast it to this struct. And then all of the access is done via getting the field from that struct. OK. Now, we need to create jump points, because we need to be able to resume the coroutine from the middle of the function. We have 2 suspend points, so we need somehow to remember which one we are at. So again, we added a field, suspend index, and just before Coro suspend, we will add index equals 0, and just before the second one, we will say suspend index equal 1. It's slightly more complicated. There are ways to be more refined where do you want to put the suspend index assignment. But for right now, let's say it's before Coro suspend. So now we need to split the coroutine into 3 pieces. We need to have a resumption part that will go and jump at appropriate points. There will be a destruction part that is going to destroy coroutines. And it will also have the switch, because potentially, not in C, but in C++, we may need to run different set of destructors depending on which suspend point we're in. And finally, there will be a initial function. Essentially, it will just be whatever coroutine has to do before it hits the suspend point. Now, those who are familiar with compilers, they will probably laughing, but I am not very familiar, so for me it was a struggle initially to do this split. But inspiration came from Michelangelo. And I'm not sure if it is exact quote, but in Russian this is translated into, to make a statue, I take a piece of marble and then cut all of the irrelevant pieces. So that's what we do. We will take your coroutine as is, as a single block of rock. Then we will clone it 3 times. After that, we will chop them up, and at the end, we will get all of those pieces. It ended up being so much simpler. The code just shrunk. So we will do it very simply. We clone the coroutine 3 times, and then we do little tweaks, and after that, we'll shake it, and it will be as beautiful. So what do we do? First, we will just clone the function as is. So this is function f on the left, and then f prime on the right. So we're going to make a resume function out of it. And for that, we just need to alter the beginning. So if our original function, the ramp function, has to preserve the initial calling convention, return type, and all of the arguments, the resume function can use most efficient calling convention, and the only parameter it needs to take is the pointer to coroutine frame. So our initial function allocates the coroutine frame and initializes it, and the only thing that we add to the resume is a simple switch, and we will take coroutine frame as a parameter. And then we clone it again and again. So we'll have 3 more functions like that. So one will be for resume and for destroy. So now we just need to do this thing, purgation of superfluities, something like that. And to do that, we need to briefly look what are those macros. What is Coro suspend and what is Coro end? So Coro suspend simply shows us 3 possible ways where we can go at a suspend point. One would be we need to suspend. So we'll say go to Coro suspend. Another one, it could be that we need to do a cleanup when we're destroying the coroutine. And finally, we can fall through and go to the next line. Now, Coro end expands into something like that. We're saying, look, if we need to free something, here's the memory you need to free, and then we will call whatever the free function C developer gave us for the coroutine. And then we fall to Coro suspend, which has absolutely nothing apart from the return value. And there is this little markup there built in Coro end, but I will mention it later. So, and what we do is simply we expand Coroutine into a constant. So in a start function, it will expand to -1, in the resume function to 0, and to 1 in the destroy and cleanup functions. And Coroutine will be nothing in the cleanup function because cleanup function is used when we decide that we don't need heap allocation. So we just need to run destructors and not to run any memory deallocation routines. And for those cases where we do have to do memory allocation, we expand it to exactly the handle which was given to us. So once we did that, again, what we did is a very simple thing. We cloned the function several times, added tiny little bit of code, and expanded a few intrinsics into constants. Then optimizer will actually clean it up for us very nicely. So we'll end up with this F, which just calls allocation routine, does some initialization, and then returns Coro handle, resume. The switch will be lowered down to something much simpler, like, hey, our index 0, and it will do print frame I, and then set the suspend index to the next value. And our destroy and cleanup will look just like that. So again, just like Michelangelo, cloned, a few cuts, shake, and boom, it's all beautiful. Now, when compiler knows the identity of the coroutine, it knows when to call fresume, fdestroy, or fcleanup. But for those cases where identity of the coroutine is not known, we will add 2 function pointers that will point at appropriate resume and destroy functions. So far, this is just a coroutine transformation. This is how we transform a function into a state machine. At this point, it's almost normal functions. There is one little strange thing there with Coroutine, which I'm keeping, and I will show you why we need that. So in addition to splitting coroutine, which is the transformation which potentially can be done in the front end or in the optimizer or even in the back end, there are several optimizations which must be done in the optimizer. And optimizers love inlining. So let's see what happens to main when it calls the coroutine. So the main looks like this. We call the coroutine F. We resume it twice. Oh. Okay. We will resume it twice, and then we destroy it. This is what F is. And when we combine, we see very wonderful thing, because now we can observe the beginning of the coroutine, marked with coro_begin, and we will see the points when the coroutine is resumed. So compiler is doing devirtualization here. And for, say, LLVM, devirtualization doesn't really mean to devirtualize virtual function. It just means that we have somewhere an indirect call, which is turned into a direct call. So since we observe now that all of the resumes and destroys are rooted into coro_begin, we can replace them with direct calls. Moreover, we can observe that coroutine is destroyed right here. It leaves no more. So now we can replace coro_begin with simple allocate, which is a stack. We'll just dump this F frame onto the stack, and we'll replace destroy with cleanup. So what it means is that if your coroutine type has RAII semantic, and RAII is great, it's like the best thing, but look, it's even better with coroutines because those things give you a heap allocation elision. So now coroutines are done. What we have is a plain function, and the rest of the optimizations will take care to disappear the coroutine completely. So first of all, what will happen is that we'll have more inlining. Since we replaced indirect calls with direct calls, and we know what resume is, compiler will inline them. Okay. Now, it needs to do this very magical thing, SROA, scholarly replacement of aggregates. So let me say a few words about that. So it looks simple to you, right? It looks very difficult to a compiler because this p.x is pointer arithmetic to get to this value in memory, and then we do a store into it. And then when we do the return, it's the opposite. So compilers hate those things. Compilers hate memory. What they like constants. So what SROA is doing, it replaces your, wait. It seems like I destroyed the slide, but let me speak through it. So what SROA is doing, it turns the members of your struct into variables. So essentially, this whole point goes away, and you will just have int, const y equal 1 and 2, and then you use them. Now, I said compiler likes consts. So there is this wonderful thing called SSA, static single assignment, which essentially you can imagine is you simply make all of your variable const. But that brings complications, because for this case, well, I really cannot mark x const. But solution is easy. We just rename it. And then all of the places after the second x, we will use x1 instead. And then some evil people use goto, right? So how do you fix that? Initially, it's easy. We'll have const in here. Now, here it's trouble, right? Because here our x is something we don't really know. And the rest goes the same. And when in trouble, compiler writers resort to magic. And the magic is they simply invented this magical function called phi. And what it does, it says, look, if I came from the block with a label entry, I'm x. And if I came from the block named loop, I'm x1. So this is how it's resolved. But what is awesome about SSA is that everything is essentially a constant value. Nothing ever changes. And this is what allows us to finish the optimizing this coroutine into nothing. So do throw, get rid of the struct, make everything into a constant. We will see here that our assignments of suspend index, they were all pushed down after the if, and I'm using this notation to explain where we call the magic phi function. So if I came from the block bb1, I'm I, otherwise I'm I plus 1. So once we did that, we run that code elimination, this thing disappears. Now we do constant propagation. This thing disappears, goes away. As soon as we got rid of the if, now we can replace the phi nodes with actual values. And then we will repeat it one more time, and we are here at the disappearing coroutine. But so far, we talked about generators. But maybe the thing you care about is async coroutines. So to do the async coroutines, I need to tell a very short joke. Essentially, rocket, on the launch pad doesn't start. So they're finding the guy who knows how to start the rocket. And he gets a hammer, naturally. He looks around, walks around the rocket, and then hits it in a particular spot really hard with the hammer. Then the rocket starts, flies away. And then he gives a bill, which is like $1 million. Like, why? The only thing you did is just like hit your rocket with a hammer. Well, because I knew where to hit. So the trick to optimizing asynchronous coroutines is just to know where do we plug those two optimizations we talked about. Because essentially what we talked about is that there is a coroutine transformation which splits it into a few pieces. And then there is another one which does devirtualization and heap elision. So we just need to figure out where to put it. So let's go back to the picture. Again, front-end, optimizer, code gen. And we already agreed that we'll be looking at the optimizer. That's where the meat of coroutine is. So let's zoom in. if you look into optimizer, it has also several parts. There are early passes which are doing cleanup after front end, because front ends are on purpose, correctly, emitting rather inefficient code. But it can be very quickly cleaned up. We already saw SROA optimization, which does a lot of useful things, converts into SSA. And then it does some kind of canonicalization. Coroutines are not there. Then there are late passes, where we do things which can potentially blow up the size of the function. For example, vectorization. Again, coroutines are not there. Coroutines are in my favorite part, and I think Chandler would agree, it's his favorite part too, is, what? There was a comment from the audience? Yes. Bless you. So this unpronounceable thing in the middle is the best. Because what it stands for, it's coldgraph strongly connected component path manager. Because it looks at your whole module and then builds a coldgraph to see which functions call which. And then it runs optimization in the bottom-up order. So first, it will optimize the leaves. They will become smaller and simpler. Then it will optimize their colors. Why to do it in this order? Well, because it allows us to do inlining. And inlining is most amazing thing which is in the compiler. It allows a lot of optimizations to work really well. And it keeps going like this. So zoom one more time. So this is what compiler does for every single box in that graph. First, it does few interprocedural passes, CGS, passes, that are allowed to look at more than one function. It can look at the current function, the next function, the function that called it, and the big one here is the inliner. So do you think, like, and after those guys are done, it will go and optimize the function with traditional functional passes. Where would you put Coro split? In the beginning, in the end, in the middle? Do you have any feelings about that? Okay, how about at the very end? No. At the very beginning? Okay, good. And in the middle? So it's about half and half, the beginning and the middle. So we actually do it almost in the beginning and at the end. And by the way, we are ignoring the coroutine the first time we see it. So it is also, it's simultaneously in the beginning and in the end. So I also put a line here with ×4. So even if we go back, everything starts essentially with the inliner. We're at the leaf. We shrink the functions, and we will see, can we inline something in? Once we inlined, we will go and clean up the function. At the very end, there is a devirtualization detector. So if any of the function in direct calls were turned into direct calls, it will restart the pipeline for the same function from the beginning. And it can do it up to 4 times configurable, but default is 4. So we will stick our coroutine split at the very beginning, immediately after inliner, and Coro allied, which does heap elision and virtualization at the very end. And let's see what happens. So our coroutine comes here. It goes completely through the pipeline. And that is one of the big ideas of how to make coroutines efficient. Because, as I said before, optimizers are awesome at optimizing the functions. They're not very good at optimizing state machines. So we're trying to let the coroutine through as the normal function all the way to the end of the pipeline, up until the point coroutine becomes eligible for inlining into its colors. So once we completely shrunk the coroutine as a normal function, while control flow is still observable, while we can propagate constants, do common expression elimination, and all of those beautiful things, once it finishes the end, we will trigger the restart. And it comes back to our core split. That's when we actually go and split the coroutine. So it'll turn into well, 3 functions in this case. Now, they all keep shrinking, and we proceed to optimizing the color of the coroutine. Okay, good. So now we're in main, the one that called the coroutine. And by the way, we already optimized and split out the little pieces. So now what is left is, you get to the inliner, it goes up. One more time. And because, oh, sorry. When we reach core allied, you remember we replaced indirect calls with direct calls. That allows, that forces the restart of the pipeline. So it goes back, and now it is at core split. So now if this function happened to be a coroutine, you can split it further. So, well, in this case, it goes back to main. So essentially, if you have a code which looks like this when a non-coroutine calls a coroutine that calls another coroutine, which calls a coroutine, then you have absolutely no heap allocations whatsoever. Okay. So let's see if you have some questions, because I have more if need to. So yes. Visual C++ is an earlier version of that. It does not do this yet as well, but it does heap allocation elision, but optimizations in LLVM are more refined. They're building up on the experience we had in the, yes? Okay, so here's the state of the coroutines in LLVM and Clang. Yes, the question was, can we use them today? You can use LLVM coroutines today. So what currently is in the trunk is LLVM level coroutines. So if you're fine with writing your own front end, or you're comfortable with writing coroutines in LLVM IR, go ahead. You can try them out. But if you want to use, say, C++, we may get the Clang compiler in the trunk soon that will emit correct intrinsics and will make it all work. And soon, hopefully, it will be in 4.0, but we'll see.
What's an example of where the dynamic memory allocation would be completely necessary?
Okay. The question is, where is an example where dynamic allocation would be necessary? For example, we are doing, we create a generator, and then we moved it to a different function, or we passed it by reference to a different function, and we don't, actually, we moved it into a different function, because now that function may run the generator and destroy it, but the caller does not as soon as you moved it out, it doesn't know. And it's caught by SSA form. We didn't even have to do anything, because we can only find this nice, very clean path from the destroy to the begin only if nothing interfered with that particular value. Because as soon as you move, you assign 0 to coroutine handle. Thus, it breaks everything, and automatically heap elision stops. And those are some of the people that were involved in the design and implementation of LLVM and Clang coroutines. So great thanks to them. Okay, so let's proceed to the next part, which is I will teach you how to make coroutines disappear. Actually, it's even better. It's even better. It stands for building better future. And here I say future literally, as in building better future-like thingy. Or if we think differently, how would we design a future if we had coroutines in the language from the beginning? And what we would like future to be, we want to enable heap elision, and we want to make future zero overhead. Is it possible? Of course, of course. So what are the overhead of the future and promise? And traditionally, it's at two endpoints, and what we are doing is we are transferring a value from a promise to a future. And what we have a memory allocation overhead, because we have to store shared state somewhere that will store a variant with one of the three possibilities which future can hold. Nothing, not yet, a value, or an exception pointer. It would need to have some atomic ref count, because lifetimes of the promise and the future are not in sync. So we would have to use ref counting to do that. And atomics are expensive, especially with multi-core machines. 10 nanoseconds, 20 nanoseconds. Also, we need to be able to synchronize setting a value and getting a value. So we would need a mutex and a conditional variable. And finally, there is an extra cost in the future that requires scheduler interaction. It comes because when we say set value, and let's say we give a callback to .then, do we execute the callback right there in line when we call .then? If we do so, potentially we can blow up the stack, because a future that we execute with .then may do something else, then will do .then on another value, and we may end up with a big string of chain of callbacks that will consume entire memory for the stack. So, so frequently what people do, they would schedule a continuation on a different thread, or possibly they defer it so that you will get to it when you actually return from the current function. And this is a brief reminder of the sugar that coroutines are doing. And those who were at the talk earlier this morning, they recognize that. For those who don't, so this is the part which is done by Clang. So when somebody gives us a coroutine with this body, compiler will discover coroutine traits, find the promise type, which is the library customization machinery for the coroutine. And after that, it will place an object of type promise on the coroutine frame. And since coroutine has to return back to the caller when it suspends, we need to know what is the thing we have to return at that point to the caller. So a get return object is the customization point which tells us what to return. We give a possibility to suspend just before we enter the body of the function, and we give a possibility to suspend before we reach the end. And also, if you want to catch exceptions, stop them, and then port them elsewhere, there is a possibility. If you define set exception, we will put a try catch around your body, capture the exception, and push it through your class, and then you decide what to do with it. When we hit co-return, it will inform your library, here's the value, and go to final suspend, label, same with the return, and just for completeness, this is what happens for the yield. Then, remember there is a coroutine frame, and there is a void pointer pointing to it. That's what was in our C example. In C++, we built a little bit of syntactic sugar around it, which just puts a happier face on the void star. And because we also place a promise at the deterministic location somewhere in the coroutine frame, if you know what is the promise of the coroutine, we will give you ability to reach into it and manipulate it somehow. For example, generator in the example that James shown, that's how you are getting current value. Okay, we're almost done. with the reminder. So, and co-await, when you see that, you generate something like that, where we give a name to an expression. We ask it, are you ready? If so, we will say, please give me the result. And here I'm using the GNU extension statement expressions, where there is the last statement is the result of the block. And if not, we will say to the coroutine, please save the state, which translate into set index, like we saw earlier. And we will say, hey, here's the coroutine handle. Do whatever you want with it. And in the end, we jump to epilogue. And two simple awaiters to show. Okay, so now we are ready to design zero overhead future, which has no of the inefficiencies that I listed in the beginning. So we already talked about earlier, if we want heap elision, we need to implement RAII. So we're trying to define a task which works kind of like a future. So to do RAII, we need to destroy it in its destructor. And possibly, when we start adding move, we also check whether Cora is nothing, and then don't destroy it. And we need a constructor. So it will look like this. And again, as was shown earlier, you don't want the coroutine to run all the way to the end and destroy itself. You need to say in the final suspend, please suspend. And then there are a few other functions which are not interested in at the moment. So to take care of the return value, we are going to put that variant that stores either a value or nothing in the promise type itself. So, and in the return value, we will emplace the value into that variant. And in await resume, we will extract that value and return it from an await resume. So now we cleaned up this one and this one. We no longer need memory allocations for the shared state, and we don't need atomics, because with RI semantics, essentially, coroutine is always there while you have the task in your hands. As soon as the structure runs, it disappears, so you don't need to worry about the lifetime. Now, to take care of the mutex and conditional variable, we need to do something funny about the initial suspend. Because why we need to do that in the future? Because the coroutine or function starts running, and it returns a future. It may complete before you call .then or before you .get. So we need to synchronize the access to this result variant. Well, what we can do, we can start coroutine suspended. We will say suspend always to a final suspend. And we will return from the await ready always false, because since coroutine starts suspended, it is never ready, or at least not in the initial call. So compiler, when it observes that coroutine is not ready, it will call await suspend, and it will pass a callback or a coroutine handle for the guy who called it, right? So here I'm looking at the case where there is another coroutine which awaits on this task. And it tells it, hey, this is my caller coroutine handle. Resume me when you are done. So what we will do, we will remember the caller, the guy who waits for us in the coroutine frame, and we will resume ourselves. So essentially, we delay starting of the coroutine until somebody gave us a callback that we need to call to when the coroutine completes. So that took care of mutex and conditional variable. We have a few little things missing. We still do not resume the waiter, because we need at some point to resume the guy who is waiting for us. And there are two potential points where we can do that. We can do that immediately in return value, but that maybe as we'll have all of the negative properties of calling the completion from set value, because at that point you cannot tail call that resumption. And tail call is when we replace a call to a function with a jump to a function. If we do that, stack doesn't grow, so we cannot explode the stack. So to do that, we need to modify the final suspend. So final suspend, instead of returning suspend always like we did before, we will do something funny. We'll return an awaiter that says, I am not ready. Then, in the await suspend, we will resume the waiter. And it is done at the final suspend point where our coroutine is ready to go away. So why it is important to do it right here? Because if you remember earlier when we looked at how co-await expanded, is that immediately after we call await suspend, we will do, well, intrinsic score suspend, which is lowered to jump to the epilogue. It means that now this part is the end of the function. Moreover, because we suspended in the beginning, it means when this code is running, we are already in the coroutine resume function. And all coroutine resume functions have the same calling convention. And there is absolutely nothing else after this call. So it becomes a tail call. So now we can call millions and millions of coroutines, one after another in this fashion, and we don't blow up the stack. So, and finally, to complete the picture, we need to take care of an exception. And how we do it? Well, we need to add an exception pointer to our variant, and we need to add one more member to our coroutine promise. And, well, almost there. So now when exception is caught, it will pass, it will store it in the promise. And finally, in await resume, we will check. If an exception is stored, we will rethrow it. Done. So this was we just finished too early with the first part. This part was like just in case you don't ask enough questions. So do you have more questions? Yes?
Does this mean that for C++20 we will want guaranteed tail call elimination like we have guaranteed copy of it in C++17?
So the question is, to make this optimization reliable so that people can actually trust it, do we need some kind of guarantee for tail call in C++20? And yes, but this is experimental. So we just put together a future. Again, the idea was, what would a future like if we had coroutine from the beginning? Not have any overhead. We need to apply them to real projects to see how they behave. Another thing missing here is cancellation model. We need that. And I think we can, there are some ideas how to do it. And if indeed it is as awesome as I just shown, I think it would be beneficial to add some language to the standard C++20 to make tail call optimization mandatory in some cases. And the same thing with heap elision. In some cases, heap elision is a must. It's a correctness issue. So we need to figure out the language to make sure that for certain cases, and the cases are relatively simple, you have to implement RAII, and you have to see through some functions. So I need to be able to inline a little bit. If we find a way to say it in the language, then yes, tail calls and the heap elision will be there for you in a deterministic manner, and then you will get free futures. Yes?
Is this futures implementation available online, or will be available somewhere?
Absolutely. So the question was, is this future implementation is available online? Well, first of all, it fits on 2 slides. Second of all, for those who are lazy, I will upload it to the GitHub, and you can try and play. And to get the most efficient compilation, you need to use LLVM and Clang version, because we did not yet do those optimizations in the MSVC.
Can you talk more about cancellation semantics?
Okay. Question is cancellation semantics. Well, did you notice that coroutines here have RAI semantics, right? And normally you wouldn't think of having RAI semantic for the future-like thing. But with coroutines, because coroutine doesn't go anywhere while it's suspended, it's perfectly fine. But what if we want to cancel the coroutine while it's in the middle of the execution? So we have currently networking TS that has this wonderful thing, IO context. And I think it is possible to work with that IO context thing, which essentially you keep passing to sockets, to other facilities, timers, executors. And that facility has actually stop and join calls. So we can maybe split it up into several parts. One of them is IO related, but another is purely a work tracker that allows to cancel whatever is associated with that IO context. And I think that's how cancellation might work. So essentially, you don't cancel the future itself. You cancel the IO context, like thingy. And then when it's canceled, it has to go through all of the outstanding IO operations and will complete them with some kind of error, I am canceled. And that will bubble up here. And for example, you might get an exception from await resume. And then the coroutine destroys all by itself. So that's the idea. And we're done. There will be another coroutine session at 3:15. I will stay here for a few moments if somebody wants to ask more questions. Thank you very much.